Associate at Canadian Institute of Cybersecurity, and today we are going to see a bit about smart grid security. Before we dig into smart grid security, let's have a look at the following video. So this video is showing us an experimental of a cyber. Okay, so this cyber attack here is actually an experimental conducted in a lab in the US in 2007. So the idea of this attack is to show that we can actually give an impact for the power grid from a cyber attack. The command here being sent as an attack is actually an offer above the regular normal of rotation for the machine. And after this attack, the machine will start to shake and then smokes. And then we will see that this actually can, if it happens in real life, then this can actually affect of human life. That one was an experimental one. However, in real life, we do have cyber attacks which are related with the energy sector. For example, Dragonfly. Dragonfly is actually a community where they would like to try to make an attack in energy sector, especially in Western countries such as Europe and North America. And this has happened since 2011. However, the group start to make the second generation of it. They call it Dragonfly 2.0 campaign since 2015, and it still happens, and it's still happening until now in 2019. So the Dragonfly group is one kind of an attack for the energy power. A very famous attack that used this idea is also happens in Ukraine in 2015, where actually the Ukrainian power companies experienced unscheduled power outages, and these outages actually impact around 80,000 customers. First they said it's around 80,000, but then they revised that there might be more than 200,000 customers being infected by this outage. The outage happens in around 3 hours. So we can imagine that if this kind of attack really happens in a wider scale, not just in a country, but in a wider scale, like several countries or even nationwide, like worldwide, then the impact is not just like for the sake of a data or confidentiality and so on, but it's more on human life, and this will give us a problem in the safety of human life. So what we are going to look today is we will start with introduction to smart grid, what smart grid is, what the components in smart grid, and then we will continue with the security in the smart grids, meaning what are the requirements for the smart grid security, what the attacks there, how the countermeasures, and we would like to see what the future of this research and development in smart grid, and we will end this with a question and answer session. So let's start by introduction to smart grid. Smart grid has several models. One of a very standard that we use is smart grid reference model. This model is proposed by NIST, National Institute for Standardization from the US. This model consists of 7 domains. The first domain related with the power flow, and the second part of the domains related with information flow. So here we see the first part is called the generation part. The second part is called the transmission part. The third part is called the distribution. And the last part here, the customer domain. For the power, the flows goes from the generation to transmission to distribution and then to customers. While for the information flows, we also have components or domains which are markets, operations, and service providers. The information actually flows from both ways, meaning we got the data from the part of the power, and we also send the controls or the commands back to the power domains. So for example, we got the data to feed the markets about the load of the being generated and the power of the generated voltage and so on, and then from there we will make calculation how we will sell this power. We have seen that these 7 domains are related with the control system, and this control system is actually called industrial control system. So what is an ICS? ICS are actually command and control networks and systems which are designed to support industrial processes. These systems are responsible for monitoring and controlling a variety of processes and operations. The ICS, the products, are mostly based on standard embedded system platform, which are applied in various devices such as routers, cable modems, and they normally use commercial off-the-shelf software. And all this has to lead to cost of reductions, ease of use, and enable the remote controlling and monitoring from various locations. So ICS is actually for a general industry. However, power, energy, which is also part of the smart grid, is also using this principle of ICS. The ICS world is actually different from the classic ICT systems, and there are challenges for that force us to adapt to existing or even create new solutions and services. A fundamental difference is the very basic of the guiding principle, meaning that for the ICT, we are really aware about the CIA, this triangle of confidentiality, integrity, and availability. However, in ICS, the environment is different. We care more about SRA, which is safety for the human, which is the paramount or the most important one, reliability and availability. So the next part of we are going to discuss is about substation. So what substation is? Substation is actually a facility along the transmission and distribution system that connects the generation and station customer. The components for the substation, there are 2 components. The first, the primary and secondary. So the primary actually related with the power and the secondary related with the cyber. So the primary, for example, switch gear, we have circuit breakers, disconnector, earthing switches. We have transformer either for voltage or for current. We have geographic information system, medium voltage and high voltage cable drums, protection and control system, and auxiliary also of power supplies. While for the secondary related with the cyber, we have substation control system, which based on remote terminal unit, or commonly we say RTU, distributed LAN architecture, serial communication, intelligent electronic devices or IEDs, phasor measurement unit or PMU, and phasor data concentrators, PDC, which actually collecting data from PMUs. This set of the secondary facilities and functionalities, these are called substation automation system, or we call it SAS. The substation also has connection to supervisory control and data acquisition, or also known as SCADA system, and the network, the whole network is called wide area measurement system. So what is SCADA itself? SCADA is actually a control system architecture that uses computers, network data communication, and graphical user interface for high-level process supervisor management. And SCADA uses conventional operating system, and because of this, they also inherit the vulnerability of the conventional operating system. The system is based on legacy system with a long operational life and consisting of devices from many different vendors, and therefore this difficulty of upgrade. The device it's geographically, normally it's spread geographically over a wide area, and these also can be points of entry and failure. The communication protocol in SCADA, the idea when it was being developed, it was isolation assumption. Thus, the security was not a priority. For example, the SCADA protocols may be using plain text messages or no authentication, which lead to vulnerabilities. And the second thing is about time sensitivity, which make it an attractive point of attack. And also for humans who operate SCADA system vulnerable to social engineering attacks or even they can become insider attack. Another interesting thing about SCADA is about the network traffic. The network traffic in SCADA is deterministic because the component communicates with other system components in a predefined manner. Because normally the data that are being sent are the data about the devices or the power and so on. And these devices will have a periodic update of what they are doing. So the data is deterministic. This is in contrast with other IT systems in which the desktop machine, servers, and other things communicate based on requests, which is a non-deterministic way. So we have seen a very brief introduction of the smart grids and the components in the smart grids, also the communication and the control in smart grids. Now we will continue with the security in smart grid. So we will first see about the reports from some vendors. The first one is a report by Symantec in 2018 about internet security threat. One of their findings, which is very interesting, related with ICS, is about the attack, which are conventional attacks, are normally also happening in ICS system. This includes in a smart grid. For example, the conventional attacks are buffer overflow or improper authentication, and they are still at the top attacks. The second interesting finding that they have is on advanced persistent threats. So these advanced persistent threats are targeted attacks, meaning that they are being devised in a very complex way. So the components in this attack is not just one thing, but it consists of several types of components for attack, and then it happens in a long period of time. One example of APTs is a dragonfly, which we have already seen in the introduction, and this a dragonfly which has happened since 2011. Their focus is still on getting and maintaining access to energy network and gathering information on how they operate. So currently what they are doing is gathering information. However, this is like already in the border, the closest to crossing the line between intelligence gathering and sabotage. The next report is from Kaspersky, and we will see the report from the threat landscape for industrial automation system from 2017. Their finding, one of their interesting finding is about distribution of vulnerabilities, which is identified by the ICS components themselves. So the top of the top two of these components which are vulnerable are the SCADA, the part, especially the human-machine interface in the SCADA, and the industrial network hardware. Another report are also from some vendors, so which are normally related with the devices being used in the smart grid. For example, Siemens. They have many types of devices which are related with smart grids, and one of an example is they provide also the portal for reporting if there is a possibility of vulnerability. For example, this one is Siemens Computer Emergency Readiness Team provides the HTTPS search portal siemens.com. An example from their report is this SSA 348629, which is published in 2018 and last updated in 2019, meaning that the vulnerability is there. And for example, the CVSS, their score base is 7.5, meaning this is a high level. 7.5 out of 10 is a high level vulnerability. The vulnerability for this case is, for example, a denial of service vulnerability, which has been identified in, for example, Cymatic PCS7, Cymatic WinCC, Cymatic WinCC Runtime Professional, and Cymatic Net PC software. Cymatic WinCC is a SCADA system and HMI systems for Siemens. So this is an example of a real vulnerability from the device itself. So if we are not caring about this, then the attacks that we have seen before as experimental, which actually can happen in real life. Now we will see the next part is what about the security requirements itself for the smart grids. We have seen already the reports that happening currently on smart grid security. Now what are the requirements of the security? In smart grids, responses to human and other emergency interaction is very critical. So it's really kind of different from if we look just from the ICT system. So the security requirements in smart grids are several. First is this about safety, which is related with humans' life, reliability, that we would like to make sure that the power is still there even if there is under attack, availability. Also, we would like to be able to give the service for the authorized people. Confidentiality is about the access to the persons who are authorized. We give data for data or the system itself only for those authorized people. Integrity, authentication, non-repudiation, and auditability, which are similar with the ICT system. So what we see here, the difference is especially about the safety and reliability for the security. The power system security itself has been defined, for example, one from a book called Power System State Estimation from 2013, is the ability of the power system to withstand disturbances or contingencies without interrupting the power supply and compromising the quality. So here, the power system security is related more on the reliability. The major components of power system security assessment itself consists of system monitoring, contingency or disturbances analysis, and preventive and corrective actions. The integration of the conventional IT system in SAS that we have seen before, substation automated systems, gives advantages such as resilience and efficiency to the power system. And also, not just the positive side, we also have the negative one, which is brings the cybersecurity issues to SAS as well, such that about the issues about availability, issues about integrity and confidentiality. Now, if we look deeper in the cybersecurity, the substation, we can see that the common vulnerabilities, attacks, and threats from conventional IT system also affect this. However, the caveat is that not all conventional IT security mechanisms can be applied directly to SAS due to the differences. For example, in the smart grids, the environments and the networks are different. One of an example of the difference is about the criticality in the time. So in a normal ICT system, we normally have a higher tolerance of the timing, but in smart grid, some of the part it's very time critical for the information exchange. For example, from the IEC standard 61850, that defines the delay constraint for messages for substation communication. They have several types, but their highest type, which is called type 1A P1, they ask for 3 milliseconds, and for 1A P2, they ask for 10 milliseconds. And these two types are used for sending messages related with fault isolation and protection. The constraints of the timing, for example, give us also the constraints of the protocols for the communication. So one of the effects, just for example, about the data is that the message here, for example, they use goose messaging. they do not use an encryption, because if the encryption, decryption, and all the system for ensuring confidentiality, we cannot really go to the 3 milliseconds threshold. So that's one example that we cannot apply the conventional IT security mechanism to the SaaS. So now we will look at the attack classifications for the system of Smartgrid system. There are many types of classification. One type we can see the classification from CIA. We will discuss several examples for this attack, the different attack in Smartgrids. Now we will first see examples for availability. Denial of service. Denial of service is a very known attack in our ICT system, and it also happens in Smartgrid. However, the difference is that not just the normal ICT denial of service like the TCP SYN attack or the HTTP, the application attack, but this one is more related with the protocol, the communication protocol in Smartgrid itself. For example, we have traffic flooding of DNP3 packet, the query flooding from the Modbus, which targeted for PLC, programming logic components in the Smartgrid, and also this jamming of the wireless sensor network related with the substations. Next, there is also spoofing attacks. Again, we have known spoofing attacks in normal ICT. However, in Smartgrid, we have also different types of spoofing attack. One of, for example, is Modbus vulnerability, where the attacks impersonate the master and sending meaningless messages to RTUs for processing resources. Another type of an attack is called false command injection. One example of this false command injection is that we reset function attack by sending a DNP3 message with function code 1 to the targeted outstation. This attack causes the targeted device to restart and make it unavailable for a period of time. Next, we will look at an example for confidentiality attack. One type is called sniffing. In Substation, the sniffing communication traffic can happen to get confidential information, such as fault records that I have mentioned before using the goose messages and MMS report events. I have said before that in these messages, the packet itself is not encrypted, so meaning that the data is plain text and can be read directly. Next is traffic analysis, where again, some of this analysis is exploiting the vulnerabilities in protocols such as IEC 61850. Next is GPS spoofing, which is by confusing GPS receivers by sending fake GPS signal to violate the synchronization. The problem if we have the violation of synchronization is related, for example, with PMU, because PMU is actually collecting data with from different places and the way they make the synchronization is by the GPS. So if the GPS is not synchronized, then the data being read is wrong. Next, we have examples also for attack which are related with integrity. A very common attack is false data injections. The requirements for this attack is that the attacker is aware of the current state of the whole system, and the meter measurements are manipulated before they are used to estimate the state. That's the requirements, and the basic principle for this attack is that an attacker chooses a non-zero factor with arbitrary values, where each value stands for an aberration from the original measurement of a meter of the power grid. So false data injection, the idea is that we want to make the wrong calculation of the estimation of the power. Next is a replay attack. The idea of a replay attack to again send the same packets again and again. For example, baseline response replay. In this attack, an attacker with knowledge of a normal DNP traffic patterns simulates responses to the master while it sends a fabricated messages to outstation devices. Another example of an attack for integrity is man-in-the-middle attack, and this happens, for example, for the controlling system and by and which can disrupt the normal activity. Now we have seen already the different types of the attacks and how we actually can detect or how can we countermeasure the attacks. Well, for example, for the denial of service attack, for the DNP3 packet flooding attacks, we can countermeasure it, for example, by transmitting shorter DNP3 packet to the receiver instead of the longer one. And for the Modbus query flooding, for example, we can do detection. And some of the researchers have already proposed, for example, the detection of this attack by using k-nearest neighbor, support vector machine, decision tree, and random forest. Another type of attack, spoofing attack. For example, for the Modbus vulnerability, we can use detection with the IDS tools. For example, some researchers propose using Snort by using a rule to alert where there is a TCP connection from external network to home network on port 502, which is reading slave device. For false data injection, there are several ways for us to make detection and countermeasure. One is when a goose packet is a new notification, it is checked against the power feedback from the SV messages, and then we will see from this one, we check again if the goose message and the SV message is within the same time frame. If this is not, then the case the probability the goose message is modified. Another way is that also the controller constantly monitor the changes in the voltage and the current waveforms, which is reported by the SV messages. And if there is a major changes detected, it is checked if the source of this event was a status change. If it is not, but then there is a good update message it received, then it possibly got blocked. So these are the possible way of countermeasure for false data injection. So we have so far seen the smart grid, the security smart grid. So what's next? Is there something still in this area? Yes, there are still many open problems in smart grid security. For example, the digital forensics which is an aspect of cyber defense that becomes essential in the event of a security breach. The problems in doing digital forensics in smart grid is, for example, in the part of collection and analysis of digital data from different sources, such as computer system, storage devices, and network stream, to investigate the cause and consequences of an intrusion or some other incidents. Why? Because we have seen before, smart grid has so many components, and many of these components generated data which are very big. So because of that, the collection is already a problem. Like, where do we collect the data? How often do we collect the data? How do we collect the data? That's just an example for the digital forensics. And because also a SCADA system must be continuously operational. This is related with power energy, with energy sector. So we would like to have this always operational. So a forensic investigator cannot turn it off to capture and analyze data. It's not like a normal ICT system where, for example, we can just shut it down and restart it. But in a real SCADA system related with power energy, we cannot do that. Therefore, we need to think about live forensics. However, the critical nature of the SCADA system, which is this operability, the availability of 24/7, makes us also need to think that we can only have forensic investigators spend as little time as possible on a live SCADA. So again, even it's a live forensics, we cannot do it online all the time. So the challenges here is, first, it is still unclear how to acquire live data on the SCADA system in a way that minimizes risk to the system services. And also, The system logging for the SCADA capabilities, they are actually geared towards process disturbances, not security breaches. So we will have many data from the logging related with disturbances with the power, but not with security. For example, I have a data set. It consists of 128 features, where 116 of it related to power system, and only around 12 which are related with cyber security features. So here we have many data which are actually about the power. Next is about scalable data collection, because as I have said before, many of these data, they produce so many measurements per second. Just an example, a sensor can carry out up to 4,000 measurements per second. So if we imagine 4,000 measurements per second, and then this always in operational, so if it's just one day data, we already have so many millions of data. And if we take a week, a month, and so on, then we really need to think about how this large amount of data can be stored, can be captured and processed. Another challenge is about the GPS spoofing attack, which again will make a wrong measurement, because again, for example, the measurement that comes from VMU depends on the synchronization from the GPS. Next, if we look at intrusion detection system, what are the problems there? Well, currently we have many advantages already from the intrusion detection system for the smart grid. For example, if it's behavior-based detection, then we can detect zero-day attacks. If it's behavior specification-based detection, then we can detect zero-day attacks and also with a low false positive rate. If it's based on the knowledge-based detection technique, then we can have low false positive and make minimal demands on the host microprocessor. For the host-based auditing, then we can have distributed control and ease of specifying or detecting host-level misbehavior. And for network-based auditing, we reduce the demand for processor and memory on resource-constrained nodes, because we are reading it on the network instead of on the host. However, there are also drawbacks which are related with the ideas. For example, the drawback is for the behavior specification-based detection, we need human. Human must be in the instruments to make the state machine or the grammar that represent the safe system behavior. And this activity is expensive, slow, and prone to error because of human error. Next, about the knowledge-based detection techniques. This technique is helpless against zero-day attacks, because we only can say, or we can only detect things which we have seen before. So we cannot detect zero-day attacks. And again, for this, the knowledge base, we really rely on dictionary that must be stored and updated. And as I've said before, the systems such as for the SCADA system, update is not such an easy one like we can do with the normal ICT system, regular updates and so on. The host-based auditing, we can have the drawback about the increase in the processing and memory on the devices itself, which are not supposed to do that for. For example, this device is like the IED system, which is with spatial kind for, with spatial goal. For example, this is for measuring for the relay measurement or a protection. So if we put this on top of the original function, then it will cause processing and memory. Next year, for the network-based auditing, the visibility of the nodes collecting audit materials may limit the effectiveness of the communication itself. So one of the open problems also in smart grid security is related with the system theoretic approach. The US Department of Energy reports that to operate resiliently even during distribution attacks and natural disaster, they say that we need to have a system theoretic approach, which means that we focus on the physical interaction between each component in the grid, And then we make a system model, for example, power flow model, sensor model, and then we also make a tech model, which are related, for example, with contingencies, sensor failures, false data injection. And for the countermeasure for the system theoretic approach is related with contingency analysis, meaning that we make an analysis of the steady state of the system itself, and then bad data detection, where the bad data detector is such as largest normalized residue detector detects the corruption in the measurement by checking the residue factor. So this is related with the power flow. So both information security and system theory-based security are essential to securing the smart grid. So I will try to conclude from this presentation. So first, smart grid is evolving, and the security issues exist in all of its domains, meaning that in customers, market, service provider, operation, generation, transmission, and distribution, each of these has a part in the security issues. Smart grids also uses conventional operating system, as I've mentioned before, and also conventional networking. Thus, we inherit the vulnerabilities from the systems. Next, the communication protocols in smart grids, for example, in SCADA, was developed before in isolation assumption, and thus the security was not a priority. Therefore, currently we need to add this security layer to the smart grid because the security was not considered in the development phase before. Conventional IT solutions may not be applicable also to smart grid due to, for example, time-sensitive nature of the smart grid or resource-constrained devices. And one way of looking at smart grid security is not just from ICT, but both from information security and system theory-based security. And the last part is smart grid security has still many open problems, and there are still many possible research and developments in this area.